All right, so let's get started. So before we start, if you guys put your kind of questions on the chat box or you come in front of the desk to ask me questions, don't forget to email your questions to the TA, okay? So you can get extra participation scores. So, okay. So this is our agenda today. Last week, we talked about physical memory management. And this week, we're going to talk about virtual memory management, including like patch table and like some virtual memory things that you need to know. And then if we have some time, we can talk about some advanced research topics. So before we start, let's first come through some Q&A. So the first question is about how does the patch allocator avoid memory fragmentation? So as you know, there are two kinds of fragmentations, external fragmentation and internal fragmentation. So for external fragmentation, for Linux kernel, they're using patch size to solve the external fragmentation. Because if you align the patch size to 4 kilobytes, like when you're doing the allocations, then the minimum size is patch size, then there are no external fragmentation in this case, okay? Because you always allocate 4 KB, okay? And then, but if you always allocate 4 KB, just like to allocate a page, then there might be internal fragmentation, right? Because like inner the patch, maybe the data cannot fill the 4 KB patch size. So in this way, like Linux use the step layer to manage the kernel data structure. So in terms of the data, actually, data structure is one kind of data that probably will not fit the 4 kilobyte because 4 kilobyte is too huge for data structure. So data structure, just like the things you already learned, just like text structure, or like last week we talked about the patch structure. So those data structure, they are usually several 10 of bytes. So it is way smaller than 4 kilobyte. So we need to say, like, if we have a step there, then we can reuse this data structure. We can group the data structure together. Okay, so this can, in some degree, solve the internal fragmentation, but I mean, it just kind of alleviate. For Linux system, it is hard to purely remove the internal fragmentation. Okay. So the second question is, why is it necessary to allocate specific patch frames to zone-DMA? So the reason is, for older I/O device, like including network cards, sound cards, these controllers, they were designed to perform DMA within the first few megabytes of memory. Because for those older I/O devices, their DMA controller has limited support on addressing. For example, maybe they can only address in several kind of megabyte of area. So this is a reason in ancient time, Linux has this kind of design philosophy, just like they are going to reserve the first several few megabytes for DMA usage. Okay. So I think this is a very similar question, is because you know there's zone DMA, there's zone normal, and then zone high memory. So I put it here to make it together to answer. So for patch frames allocated to user process, they are all belong to the zone-high memory portion. Okay. So usually people are saying there are low memory and high memory in the physical memory address space. So for the low memory, they are using static mapping, and their classification will be the zone-normal. And for high memory, they're using dynamic mapping. So dynamic mapping means they're using patch table, right? Because patch table is not a fixed mapping. And static mapping, you can think about just like the virtual address to physical address is a 1-to-1 mapping. So you can think about physical address 1 plus 1 offset will becomes, virtual address plus 1 offset will becomes the physical address. That will be the static mapping, okay? And why is the kernel limited to mapping only 128 megabyte of high memory? So the reason is, in a 32-bit Linux system, the kernel can only address 2 to the 32 virtual memory address, right? Because it is 32-bit. So in Linux system, they can only address 232, and 232 is around is around 4 gigabyte. But because for the user process and kernel, they share the same virtual address space, right? So in this case, kernel can only use the topmost 1 gigabyte. Okay, so this is part of the reason, like because there are very limited resource for kernel, and inside this one gigabyte, there are at 96 megabyte, they're using static mapping. That is, they're using this zone-normal. Okay, and usually the kernel code, the kernel function, in most of the case, they'll be stored in this at 96 megabyte area. So there is still 128 megabyte left in this 1 gigabyte area, and those are being used for the dynamic mapping. So in some cases, maybe kernel need to get some like dynamic kind of parameters, or like to have some dynamic design layer, then 128 megabyte can be used in a more flexible way. So how does Linux alleviate race conditions when serving multiple interrupts? So last week, at the end of the interrupts slides, we are talking about the top halves and bottom halves. And splitting interrupt handlers into top halves and bottom halves is one of the policy to solve this kind of race condition if there are multiple interrupts, because the most critical things that need to be finished will be put into top halves. And for those that can be delayed, they can be put into bottom halves. So even both top halves and bottom halves, they are belonging to the interrupt handlers, but only the top halves needs to be finished at the time that the interrupt handler is called. Okay, so the rest of the bottom halves, they can be due in some time, like system is during the light loaded time. Okay, so this is about the way Linux used to alleviate the load when there are multiple interrupts here. Okay. So the same things, we'll also do a recall for the last week, like we talked about the physical memory, because there is some relationship between physical memory and virtual memory. So we'll first do some recalls. So the most important things for physical memory and virtual memory, they are patch. Like patch frame is for the physical address space, and patch is for virtual address space. So they are all in the size of 4 kilobyte. Okay. So for patch frame, like you already know, like in the physical address space, if it is kind of the 4 gigabyte or like whatever you want, depends on how many DRAM there are in your systems, then they will be allocated, they will be split into a lot of 4 kilobyte chunks. For each chunk, it is called patch frame. Okay, so usually in the 32-bit systems, the first 1 gigabyte that are used for the kernel address space, and the rest of them, they're used for the user address space. Okay, so you can think about the kernel code that are placed in the kernel address space, and the user code they are be placed on the user address space. Okay, so when you're running a program and the program is going to call the memory allocation functions, and kernel will allocate a patch frame in the user address space, and then kernel will update the patch table. So this part will be explained later, how the patch table works. Okay, so we'll skip this part. So next we would focus more about the patch frame part. So although the processor's smallest addressable unit is a byte, current system using MMU typically deals in pages, so usually it's 4 kilobyte. And we also show you the data structure for the patch frame. Like there are several kind of fields that are going to describe each patch frame. So this is the data structure that we are using in Linux kernel. And we also do some calculation to say, hey, actually for each field, maybe it is like 2 bits or 4 bits. So it depends on which type it is. So you can do some calculation. So like for this data structure for only one patch frame, there will be around 40 byte. And then if you have a lot of patch frames, so there will be some overhead there for the systems. So we also talk about like when we are going to do the memory allocations, actually we not only focus on the patch frame part, we also need to consider some memory characteristics, right? Because different memory systems, they have different structure. So we talk about there's UMA structure and the NUMA structure. So UMA is there is a memory controller between all the CPUs. Okay, and then for NUMA structure is we move the memory controller inside the CPU. So each CPU they have their local memory and remote memory. Okay, so in this way, actually, CPU accessing local memory will be faster than accessing remote memory because the distance is longer for accessing the remote memory. Okay, so in terms of this structure, we need to consider the memory node. So the granularity when we are doing the memory allocation, we need to follow this node, zone, and patch frame. So for nodes, it's about when we are going to do the memory allocations, we are going to see, we're going to understand the structure of CPU and memory. And if the process run in this CPU and it is required for some request for some memory, the memory will be allocated from this DRAM if it is possible. So this DRAM has higher priority to be allocated to this CPU. And this is the nodes part. And zone parts, you already know, just like there are 3 different kind of zones, like zone dash, DMA, dash normal, and dash high memory. So different data, they need different kind of service. They're going to be placed in different zones. So under the zones, the smallest granularity will be patch frames. Okay. So, but as you already know, like even we do this kind of hierarchy, actually zone dash normal, there are 800 something megabyte there. And zone dash high memory, there are way more than several gigabyte. So it is quite huge. In this case, how to do the memory allocation? So in terms of Linux, like if we are going to do the memory allocation on the physical DRAM, there are 2 kind of way. One is for user space memory allocation. The other is for kernel space memory allocations. So no matter which one that we are focusing on, they use the same allocator. Low-level memory allocator is called a allocate dash pages. So if you are familiar with Linux, you are already heard, if you are familiar with Linux, you may hear the key term called the body systems. So body system is implemented in this layer. Okay. So between the kernel space memory allocator and user space memory allocator, there are also several allocation policies here. So for kernel base, actually, you can use the K-memory allocation to work with the slab there if you are going to allocate some place for data structure. Because data structure is usually smaller than 4 kilobyte. So in this case, it will be a better fit to pick the K-memory allocation, like the kernel memory allocation. Okay. And if you are going to allocate for a larger space, I mean larger than 4 kilobyte there, then vMemory allocation will be a better fit here. So for me, vMemory allocation, it can make sure the virtual address becomes continuous, but the physical doesn't need to be continuous. So this is for kernel part. And then for user part, like when you call the memory allocation, the C library here, actually there are 2 different ways to do the memory allocation. One is called BRK, the other is called the mmap. Okay, so no matter mmap or BRK, they're just trying to, they will call the allocate dash pages to get the physical memory from the DRAM. Okay. So body system, we also talk a little bit about it. Just the key concept behind body system is to make sure the allocation unit is aligned to the 2 to the order. Okay, so here is an example is if a process requested a 2 to the 2 block, but there is no free patches in order 2 and order 3. So order 2 means the blocks maintained in this order 2 layer is 2 to the 2, and order 3 is 2 to the 3. So they are all continuous. So what I mean continuous is if it is 2 to the 3, then it means like we have add 4 KB memory patches that are continuous in this layer. So in this example, if like you are going to if a process is going to request a 2 to the 2 and there is no in order 2 and order 3, then Linux will check for the order 4. So for order 4, maybe we'll get one piece of the memory, like 2 to the 4 blocks here, and we will split into the half. Okay, so when we split into the half, then we can reserve the 2 to the 3 in this order, the layer 3 here. and the rest of the 2 to the 3 can be sent to the next lower level to 2 to the 2. Okay, so because the process only needs 2 to the 2 blocks, so the half of the 2 to the 2 to the 3 can be allocated to the 2 to the 2 the process, and the rest of it can be reserved for the data structure. So next time, if there's another process comes and it requests for the 2 to the 3, because we already have 2 to the 3 here, then the body system will directly allocate this part to the process. So this is the body system. Actually, the key concept is just about to always do the allocation aligned with the 2 to the 2. Okay, sorry, 2 to the order. Okay, so slab there. So when the data structure is no longer needed, it will be returned to the free list instead of deallocated. So, sorry. Okay, so what I mean for data structure is these kind of things. So this one is for text structure, just like it is going to describe the process, or like PCB you already know in the undergraduate class. And then this one is used for the kind of semaphore. And then this one is for like inode. This is for file. So actually different kind of data structure, they were in different size. So if we mix those of data structure together and then to put it into the patch, probably there will be internal fragmentation, because you can image like if there is text structure and a file, but file is quite large and they are placed together. But if the text structure, I mean, if some process they are free, I mean, if we terminate some process and they free up their text structure, and in this case, actually, this memory slots cannot be used to store any other like inode data structure, because inode is larger than text structure. So in this case, why not just split it? Why not just group those text structure together and put in one patch or like several patches? In this case, we can reuse the space to store the future like text structure. And the same things for like inode, there are the same things. Actually, those data structure, they cannot, usually they will not be more than like 4 kilobytes. Usually there are several 10 to 100 of bytes there only. So the key concept of slave there is just to group those same data structure together and then to locate on the same patch, or like on the same few pages. Okay, so actually the stuff that acts as a generic data structure caching there. Okay, so for data structure caching, it's just because like, sorry, okay, here. So caching is just about, come to think about if this is a patch, oh, sorry, if this is a slab and instead there are several patches. So those patches, they will only store text structure in this case. So if one of the text structure is free, then we will not really remove this area, because in the future, maybe there are some new process that are created, then they can directly reuse this text structure, because all the process, they have the same text structure. The only difference is the field. I mean, the value of the field will be different, but they all have like PID. They all have like those kind of fields. So we can directly reuse the space. Okay, so this is the idea behind like what we are saying, like this is a generic data structure caching there. So this example, I will not go through it. We already go through it last time. Okay. So actually, there are two common libraries to allocate kernel memory. One is the K memory allocation. The other is the V memory allocation. I think the key difference between them is K memory allocations is using the static mapping, and V memory allocation is using the dynamic mapping. Okay, so what does it mean for using static and dynamic mapping? So like here, so the figure on the right-hand side, there are two different address space. One is virtual address space, the other is physical address space. So for the virtual address space, the top 1 GB, usually it is for kernel. So for this 1 GB, actually you can see like there are from 3 GB to around 3.896 megabyte. There are, sorry, 3.896 GB there for the kernel core or data, and they are using the K memory allocation. And then for this high memory area, I would say like for this more than 3.896 gigabyte area, we are using vmemory allocation. So as I mentioned in the prior slide, like k-memory allocations, we're using a static mapping, and this is the dynamic mapping. So the thing is like this. If we're using the static mapping, then we should allocate a continuous physical address space here. So from 0 GB to at 96 MB, they'll be continuous. And the address here and here, we can use this simple function to do the calculation, just like the physical address equals to virtual address plus some predefined offset. Okay, we just make the offset, and then this area can be directly checked directly. So it is super fast. You don't really need to check the patch table, right? You can just directly do the mapping, then you can know where the data is. Okay, so this is the static mapping part. But for the dynamic mapping, it doesn't really like this. Dynamic mapping, usually we use the patch table to do the translation. Okay, because you see like here is so huge. The area here is so huge, but here we only have like 128 MB here. So actually, there are also several other processes that will share this area. So in terms of the virtual memory, we need some translation there between them. Then the translation there is called a patch table. Okay, so actually this is how the difference between the static mapping and dynamic mapping. Okay, so I think this high memory is not that super important. So I think I will just skip this for the recall. Okay, so today let's talk about the virtual address space. So on Linux, each process is given a unique and flat 30 or 64-bit address space. So what do I mean for unique? Unique is process can have different data at the same address in their own address space. So process can also share address space like thread. So actually, for each process, they don't really need to care about some other process where the physical address they are using. They can just directly work on their virtual address. Okay, so this is in terms of the process point of view. In the process point of view, it doesn't really know how other process works like. And system, system means the Linux kernel. Linux kernel can help out dealing with this confliction. Okay. And flat means like the modern Linux system doesn't use the segmentation here. So just like if you have took the undergraduate operating system, you may see there is another kind of memory management. They're using segmentation. But in Linux here, we are not using segmentations. We're using a flat memory. Okay. So memory address is a particular value identifying a specific byte in a process address space. So come to think about, if you are using a 32-bit address space, then it means like you are able to address 2 to a 32 byte, right? Because in current system, in current CPU system, CPU are using the byte addressable. So usually memory we can address in a byte. So for each 32-bit string, it is possible to directly address which byte it is. So in terms of using 32-bit system, the maximum will be the 4 GB memory address space. So I think those are just definition stuff. And I want to let you know, if you have a C program now, I think this is a very typical C program and it's quite simple. And how does this C program be placed on the memory? Because when we are going to run a C programming, we need to load on the memory, right? And CPU can fetch the memory and run a C program. Okay, but how? So coming to our virtual address space, okay. So for each virtual address space, they're only dedicated for a process. Okay, so when this program is running, then it becomes a process. Okay, so we use a 32-bit as an example. Like the top 1 GB is the kernel, and the bottom 3 GB is for the virtual address space. So kernel, just like you already know in the last class, there are some kernel code, those kind of things. And then how about for virtual address space? So first of all, there are text section. There are data section and there are BSS section. So text section, you can think about it's just like after you're doing the compiling, those kind of things, you'll get a binary, you'll get an executable file. So the binary and executable file will be placed in these text sections. Okay, so you can see the example here is the code. So the whole code, I mean, there's a simple string, and then if you go in the compiler, those kind of assembler, you can get a binary. And of course, the binary will not look like this. I mean, there will be a lot of assembly language there in the binary. So this is for text section. And then for data section, actually, there are two kind of data. And this is data sections, no matter it's data section or BSS section, they are all for the global variable. So global variable like here, like they are outside the function, like int global 1-x here. So there are two different kind of global variable, initialized or uninitialized. So for the initialized one, just like you give it some value for it, they'll be put into the data section. And uninitialized ones, they'll be placed in the BSS section. Okay, so actually, like you can think about data section like when you are compiling the code, actually, if you already put the value inside the code, actually it will take a little bit space of the executable file. Like, right, because like if you have this kind of global -y equals 10, you need to be compiled into your executable code. Then when the program is running, actually we need to find where it is, right? Okay, so the BSS section is about there is no initialization. And usually in the systems, I mean in the compiler phase or like in the executable phase, there will be doing some default initialization. So usually it will become 0, usually. Okay. And then there is a user stack part. Okay. So there's a user stack. User stack that are used for storing those parameters or functions things. So usually in the main function, there are several uninitialized parameters here, and they'll be put on the user stacks. Okay, so you can think about most of the data that relate to the function, they'll be put on the user stack, including the function pointer, they'll be put into the user stack. Okay, and also the heap. So heap, their users serve for the dynamic memory allocation. So kind of think about there is the memory allocation here, and we are going to have the 20 byte here. And the 20 byte memory allocation for this P will be put into this heap area for using. Okay. And the last one is the library. Actually, when you are writing this hashtag include standard IO library here for C code, when you are going to use a printf function, a scanf function, actually this library, it is called a shared library because all the C codes can share this like standard library, right? So this shared library will be mapped into this memory mapped area. Okay. So this is how when you have this kind of C code, then how will it be placed on the virtual address space? So I still need to emphasize again, this virtual address space only for a process. So each process has their own virtual address space. So if there is another process, another C code, then you can get another virtual address space. So this is the reason that I say when you are doing the programming, you don't really need to care about if there are other processes running in the systems, and you don't really need to care about where the data is located on the physical address. Okay, so because kernel will help to do this mapping, and kernel will help to solve the confliction if there is two virtual address point to the same physical address. Okay. So actually, not every address is legal. Intervals of legal address are called memory areas. And actually, we will have more examples for memory area later. So actually, there are several permissions for different memory areas. Then we'll talk about it later. So actually, when we are going to deal with this memory management things, like, for example, what is the size of the text section and what is the size of the heap? And because heap is for dynamic mapping, so maybe heap will grow and stack will also grow in these directions. So actually those kind of things, how to handle them. So we need another data structure. So actually this is called data structure. So this is a memory descriptor, and this is for the virtual memory. So if you still remember last week, we have the patch structure. The patch is for the patch frame. Okay. So this is a kernel data structure for managing the process address space. So you can see there are a lot of different kind of field here. So there is two very important things is there is a things called star mmap and mm-rb. So actually this star map and mm-rb actually even there are different data structure, there are different fields, but actually they are referencing the same content. Okay, so like this, they are saying about what is the size of this and what is the size of this. So actually, they store the same content. The difference is they're using different data structure. So the reason is there are two different ways when we're going to access this virtual memory. The first is about maybe we are going to traverse all the virtual memory, right? If we are going to traverse all the virtual memory area, then linked list will be a better fit here. And if we're going to search for a specific memory area, then tree base will be a better fit. Your tree can return us like log n time to get the virtual memory out. So even they are kind of storing the same contents, but because they're using different data structure, so they can provide this different functionality. So if the user now is going to traverse, for example, if we are going to traverse, if there is a free virtual memory area that we can use, then we can use a linked list to do the traverse. And then if we are going to identify, if we are going to locate a specific like virtual memory inside this heap area, then we can use this mm-tree1. Then we can quickly get the virtual memory address. Okay. Okay. So maybe you have one question is, so in Linux, how can we access this structure? Actually, at the very beginning of this course, when we are talking about the process, inside the process descriptor, the text dash structure, there is a field called field. So the field will be directly point to this data structure. So when Linux is dealing with the process, it is possible to also control the memory descriptor part. Okay, so this is just I think it's not that quite important, but I think it's quite interesting to let you know. Okay, so what is virtual memory areas? Because we talked a little bit about VMA in the prior two slides. So the virtual memory area, or VMA for short, describes a single memory area over a contiguous interval in a given virtual address space. So I think the key thing is contiguous, just like a contiguous virtual address space, it is called a VMA. So this one is a crop figure from this. So I only crop out the, I think it's not here. I think it's in the bottom of this kind of structure. Actually, part of the structure, there is things called like, okay, here. So MM here, like actually you can get this more data structure if you expand out here, because like this is like the type of the MM is the VM-area structure. And inside this structure, the definition is here. So there are several fields like related to this MM. Okay, so what does those fields mean? The key important thing is here. There are three different fields, the start, and next. So for one memory descriptor, the MM structure, the start field will point to the start for this virtual memory area, okay? And the end will point to the end of this list, okay, like this. So inside the virtual address space, actually you will see things like this. Here, you can use the mmap to point to the VMA start and VMA end to locate one virtual memory area. And this is another virtual memory area. And this is the third one of the virtual memory area. So they should be continuous, okay? So if they're not continuous, they should be in different virtual memory area. Okay, so for each virtual memory area, they are consisted from several pages. So here is one VMA, another VMA, and the third VMA here. And then each VMA, they can be used just like this. Sorry. This. So this heap area, actually, there are several VMAs here. And these text sections, they can be also several VMA. Okay, so VMA just means the smaller granularity for this, like text section, user stack, memory mapping, like this kind of stuff. Okay, so this is for the virtual memory area data structure part. Okay, but I think it is hard to link the text sections and the kind of heap stack with this structure. So I do some example, maybe it can be a little bit helpful. So here is the process virtual address space we already know. There's text section, data section, BSS, heap, like memory mapping, and user stack. Okay. Oh, here's one thing that you know. Actually, in Linux, there's a keyword called anonymous. So anonymous means there is no file packet. Okay. So what does no file packet means? So if you see here is a text section, right? So when we say text section there is a code. So the code actually it is stored in the storage device, right? So this is called file packet. Code just like when you write a C program, like a C code, then there is a file. So this is file packet. And data section is because inside your code, actually you do some initialization. So actually this is also file packet. Okay, because you already do the initialization, so we need to store it somewhere. And in Linux, there will be stored inside a file. Okay, but BSS section and heap, actually they are uninitialized, or like they are dynamic kind of parameters. So they are not defined in your code. So there's no place to store this kind of information before you run them. Okay, so those are no file packet. I mean, they are generated in the runtime. Okay. So let's start from the very beginning. Like, in the point of view of one process, actually you will have their text structure. The text structure is going to describe that process. Okay. So inside the text structure, there is a field called MM. So MM can point to the virtual memory structure. So in the virtual memory structure, actually there is an mmap. So sorry, this one. There is an mmap pointer. So the pointer, sorry, the mmap structure. So inside this structure, there are several fields here. Okay, so let's get started from here. Okay, so actually for the mmap, there will be point to the first like VMA. So the first VMA there is start and end, right? So this VM-area structure, there are several permissions here. So it is possible to say, hey, this is the read-only sections, and this is also executable, right? Because this code cannot be modified when you are running. So this is read-only. And because this is the binary executable file, so this is VM-executable to say this is an executable like things here, okay? So there is also some field is about if this is a file packet, then we need to know where the file is, and because this is a executable file, so Linux they'll be put into the /binary/executable, then you can get the executable file. So the C code is put in this like in this folder and in this position, okay. So the same things for data sections. Actually, data section they're used for the initialized global variable, because the initialized global variable they're also stored in the code. So and the same thing, there is a start and an end. So even in this example, I draw in the same size. I mean, this one and this one is in the same wide, is in the same kind of size, but actually it depends. I mean, it is possible this section becomes kind of wider, larger. It is also possible. Okay. Okay, so the next one will be the BSS section. So BSS section is going to use for those uninitialized global parameters. So because it is anonymous, so actually we don't have the VM file pointer here. Okay, so there is no file packet. So it means there is no file pack for this one. Okay. And the next one is heaps. So for heaps, actually, it is also another anonymous memory resource because it is created online. Okay, so actually you can see like for from the data section to BSS and heap, they all support read and write. Okay, because they are kind of, you can write the data inside those sections. Okay. And again, because the heap is anonymous, so there is also no file bucket here. Okay. Okay, so like if the heap is not contiguous, because actually these three usually will not be too large because they are all already known before. When the program is running, you will use a compiler to do this kind of optimization. But heap is a little bit hard to do the optimization because heap will be allocated in the runtime. So probably we will get a lot of non-contiguous VMA. And in this case, actually, you can use a chaining to chain all this kind of VMA together. Okay. So the same things, like this one is for shared library. So just in our prior example, it would be like our standard C library. Okay, because this is a standard C library, so you can also write it. You can only read the standard library and execute the standard library. So of course, the standard library is file bucket, and the link is usually under the /library/ like this kind of share object here, libc here. Okay. Okay. So the last one will be the user stack. So user stack, because it is going to grow from the top to the bottom. So like here is there will be a flag here to say, hey, this is the growth down like VMA structure. Okay. So actually they are all VMA, but they are used for different function. So it depends on what kind of data you are going to store inside and how the data structure is going to manage them. But basically they are all the same. They are all VMA. Okay. So here are some more details that you need to know for VMAs. Any two VMAs cannot overlap with each other. So actually, if there are some overlap, like you can call the find -VMA to get the nearby VMA, and then to check the end field. So if the end fields overlap with each other, you can merge two VMA together to get one VMA. Okay. And how to create or expand a VMA? Actually, there is a function called do-mf function. Then in this function, you can add an address interval to a process address space, and then expand an existing memory area or creating a new one. So actually, if you still remember, there is a thing called BRK here. Actually, BRK here is going to extend the VMA size. So BRK here, how does it work? Like this. If you use BRK, usually you can adjust the heap size. So I mean, heap will be belonging to, will be back to several VMA region, right? So if we are going to enlarge the heap, you can say you are going to adjust the VM-n here, this one. If the VM-n becomes larger, then the VMA will become also larger. So actually the BRK is going to adjust this VM-n. Okay, because the start position cannot be changed, but the end position can be changed if there is some virtual memory address there. Okay, so BRK is just going to adjust the VM-n. So usually there's another thing is called mmap. So usually mmap here is going to allocate a new VMA. Okay, so this is the very kind of briefly things that you know. Okay, so this is the do-mf function in Linux. Actually, there are several fields here. The first one is the file. So if there is no file, then it is called anonymous. But if this is a file bucket, just like the data section or like the code sections, then you need to give it the file. Okay, so initial address for finding available space. So there is an address here for finding, and then there is a permission. So permission, just like here, this is a read-only or like read-write possible, or like this is the executable. So there are all the permissions. Okay. Okay. So also there's a file offset here. So if there are a file offset for the backup file part. Okay. Okay. So there is another thing is the memory dash user and memory dash count. So we already finished introducing this dash mmap things. So this is a key important things for this MN dash structure that like we're going to manage this virtual memory area, right? So there are two, I think it's quite interesting things to that you know is here is things called mm-users and mm-count. So mm-users means number of threads sharing this data structure. And mm-counts means number of processes sharing these data structures. So why they are sharing? So remember, when we are going to fork a process, we are using a copy on write, right? So when the process fork another process, at the very beginning, they will share this mm structure. Okay. And for threads, of course they will share because like when a process is going to create several threads, all the threads created by this process, they are using the same structure. Okay. So we need some counter to count about how many threads or how many processes that are using this data structure. Okay. So let me give you a quick example. So in the initialization phase, actually, if process one has 5 threads, so in the MM structure, like the blue part, MM-users will be 5 because of users means how many number of the threads they are related to this MM structures. But because there's only one process called process one here, so the MM-counts will be 1. Okay. So after the first step, the second step is process one is going to fork another process called process two. So at the moment, process one finish forking process two, then what you can see is process one and process two, they all share structure. Okay, they share the same structure. So at this moment, the user part becomes 6. Okay, because process two is created. Okay, so as we already mentioned several times in Linux, actually there is no very specific kind of differentiate between process and thread. So actually process and thread in Linux is about how many resources they can be used. So for process, actually they have a lot of isolated resource. They don't really need to share with others. But for threads, they need to share with others. So they are all executable instances. So this is a reason in this example why when process one forks a process, but mm-users still increase 1, right? Because according to the definition, mm-users is number of threads sharing the mm structure. Okay, but in this example, mm-users still take 1. So this is the reason, like in Linux, there is not that specific definition between the there is no specific difference between the threads and process. So you can also think about MN-users is just like how many executable instances they are sharing this MN structure. Okay. And MN-counts, of course, will be 2 because there are 2 processes here. Okay. So, I mean, there is one interesting thing is in the prior stage, there's process 1 has 5 threads. So why after doing the fork, we only fork 1 process out? I mean, there is no other threads that are going to be created. Because we say in Linux, when we are doing the fork, actually we'll copy most of the resource like the parents have, and including the threads, right? But according to current multi-threading implementation in Linux, actually we don't do these things. So only the calling thread is duplicated via the copy on write. So probably if this process has 5 threads, and if this process is going to fork a process out, then probably there is only 1 thread that calls the fork, right? So that thread will fork another process out. So there will not be 4 processes or like no 5 threads be copied out. So this is because like Linux doesn't want to deal with the very complex race condition issues. If it really forks five threads out during the forking, then there will be a lot of race condition issues here. Okay, so I think we can stop here and then come back after 10. Okay.
好像是
哦，对，我们跟你们讲，对，周四应该看你们要咪还是要直接停掉都可以。对，我可能就看每个人状况。对，所以就看你要咪或停掉或改日期，我都可以。对，对，好，我再问你好了。对，但周四我早上我也不行，早上我应该在开车，看一下哦。
因为我平常是下午2点，就是这样。
我觉得如果我跟你约的话，我可能会改成约什么3点之类，避免塞车，因为我去高雄。对，然后我再问你，如果你不行的话，或者是你想要改别天，我也可以。对。
那时候一样的是，我印象中好像在不同的系统里面，
对，
时常会，或者就是你在睡觉的话，还有可能是也是复制5个，对，在不同的系统。
对，但我看 Linux 它只有对，因为我查了一下 Linux 好像只会有一个对被复制出来而已。对。
那我没记错。
对，谢谢。Yep.
So, I think it's on slide 7 or 9 or something like that. So when we,
This one.
yeah, exactly. So when we load from the memory into the CPU, what is the CPU doing while it's waiting? Like, is it idle or does it actually do something?
Oh, I think the simple answer is CPU is waiting here. If it is load from the memory, but a little bit more complex answer is CPU are not really idle here because probably there are some other tasks that CPU can run.
Yeah, right. Because we're wasting a lot of time because otherwise we could schedule it to like load faster and then we have another one that we load in.
So actually there is a like store buffer inside the CPU to store the prior instructions if it is not ready to finish. Okay. And maybe there is some like very large instruction window to first do some prediction about what we are going to run. Okay. So, but I mean, the short answer will be if those tasks they are finished, then CPU will become idle.
Okay.
Yeah.
Also for the for the non-initialized variables, like the data part. So once we initialize the global variables, will they change where they are stored, or they are still stored in the non-initialized?
Yeah, they were stored. Because this, sorry. Because this one, like we say on the initialize is about when it is approved.
Yeah.
So after it is using assigning the parameters, it will be in these sections. You will not jump into this section.
Okay, so it stays there.
Yeah.
Right? So that's why we allocate the amount, I suppose, with saying what data type it is. Right?
Correct.
Yeah. Thank you.
Thanks.
你可以来试试看，这个地上会是怎么样？就是
可以，就是这个资料结构其实是要去追踪说，你看你下面的页的 VMA，其实你很多 VMA。
对。
那这个的 structure 展开来其实长这样子，所以还有很多 field 在做。
哦，所以是它展开变这样。
对，因为它都是用同样一个 structure。我现在只是把这个 VM-area 的 structure 再把它打开来，秀给大家看，说这个资料结构其实它的 structure 长这样子。
然后 star map 它是会用指哪里？
对，就是它这个 MM 会指到第一个 VMA， 然后这个第一个 VMA 它会有 VM start。
这个 MM start， 那这个是它是它是 physical address 还是 virtual address？
这里都是在谈论 virtual address 的状况，就是 virtual
那
address
为什么会
怎么管理？
为什么会是这样子的？
你说，
对，它是然后再像这个，然后再这个，为什么要做间接的东西？就是这个。
哦，没有，这个只是资料结构的示意图而已，就是这个资料结构在执行之后，它会就是去描述说这个 VMA 它是怎么分离的。对，所以它其实只是在描述说这些 VMA 是怎么被 kernel 去做管理。
那这个东西的话，这边是 anonymous 这边是说什么？就是
anonymous 就是 它的
我刚才听到说那里也有 quote，但是没有听很懂。
就是它没有 file，它不需要在系统里面有 file 去做储存的动作。
嗯，
因为我举例来说好了，你这个程式码一定要有个档案在那边，才有程式码，
对，
所以它就是 file backup。但是这个 heap 是动态的时候，它会生成那些 parameter 这些的，所以它是动态产生的资料。
比较这里比较像是一个什么？就是 Hip 那时候听你在嘛，就说是一个
heap 就是你写 C 的时候，你用 memory allocation 这种的，然后你就会宣告出很多那个基体位置，然后你可以去放资料上去。那些东西呢，都是在基体里面，所以它在储存装置里面是不会有备份的。
哦，
对，那有备份是，例如你有 file 才会有备份。
比如说是什么？比如说这个吗？就是 X chart，像这样。
应该是说这个只是说指标指到机体那个位置，可是，在机体里面的资料，它有没有在储存系统里面有一个备份？那 heap 是不会有的。
哦，
对，那这个下面这个，
那我什么时候我叫什么指令出来？通常叫最常见什么指令出来，它会
是这个吗？就是 MALOC 那个。
哦，
或者是在 C 加就是什么 new 这种。
MALOC 这里的话是
动态分配集体。
哦，这不是 physical 它是 physical 还是？
你说它分配哦，它分配的是 physical address 没错。对。
哦对。
只是说，因为你 physical address 你一定会需要在程式码这一端，你还要有对应的 virtual address，所以其实这两个是同时会，不能说同时啊，就是说它会发生的是会有情况。
是 kernel space， 然后 log 是 user space。
这样说是没错，不过因为这边的探讨都是，我如果像 memory location 我要分配的时候，我需要从 virtual memory 跟 physical memory 都分配出一段记忆出来。那这边是主要在探讨 virtual memory 的状况。所以 physical 那边的话，基本上就是前一套就是用 body system 就可以管理了。
所以现在
对，所以现在都是单独只探讨说，那为什么你刚才写 KML？我说也没有错呢，因为 KML 也会有 virtual， 只是说它是 static mapping，所以它的 virtual 跟 physical 会直接对应下来，它会只需要加个 offset。
前面说的这一段吗？就是说这个 mapping 是直接说这一段吗？
对啊，这就是它本来就是它的 virtual 本来就这边啊。所以它不需要什么动态分配，它就固定就是这一段给你用。
很需要。
我想问一下，这个 unique 是什么？就是 Steven 的 unique，
就是每个 process 不需要担心其他人也是用这一个集体位置，独特，就是每个人有他自己独立的，
就是一个 process 就有一个。因为我看它的定义不是写 have different data in the same address，
这是说，假设你今天两个 process 你有不同的 data，可是你是放在同一个 virtual address 上面，那
可以，
那是可以的，因为它是 virtual，因为它是虚拟的，所以对 process 来讲不会有问题。那对系统来讲呢，它会帮你去做 redirect，所以它真的会帮你放到不同的实体的地方去。对，所以系统会避免这件事情发生。
如果我们写程式，就像我们知道是同一个，我们知道同一个，会自动分开。
没有，你写程式跟他写程式，你们两个人写不同的程式，可是你们可能都对同一个机体位置去做程序。
对，
但系统不会让这件事情直接发生。对，就是你程式设计师不需要去管这件事情，系统会帮你去做容错这件事情，就不能说容错，就他帮你去做 redirect 这件事情。对，
反正就是
到他会自己去做。
对，就是 virtual 的概念，你可以想象成就是你在写程式的时候，你想象中的机体长什么样子。那 physical 就是实际上 CPU 看到的 DRAM 上面长什么样子。
对，所以这边就是在说 virtual address 它可以存在同个地方，只是实体就是不一样的地方。
对，这是不一样的地方。
然后还有
这是讲的是两个 process 哦，同一个 process 当然不行。
好，
对，就是在同一块 virtual address space 里面，它是不能有冲突的。理论上啦，就当然有一些例外，但是那个就先不讨论。
好，然后那这个 let 是什么意思？
就是你可以想象成它就是一个就是0到4G 这样子，它没有再去切断说，这一段是拿来干嘛？它有点像是什么 zone dash DMA 那种感觉但是不太一样，就是它是在一般大学部都会学到作业系统里面会学到其他的作业系统，它会有可能会有这样的设计出现。对，就是很早期的一些系统里面它会有这样的设计。
好，然后看一下，因为我在想这个值的位置有关系吗？就它一定是第二个位置会指到 end 嘛？因为这不是写第一个是画到 start， 然后第二个，然后最后一个
其实只是因为对我是想说 start and 这样子而已。
就是没有特别
关系。对，没有特别关系。
看一下，
所以它有两层结构的意思，这是什么？它有两层结构的意思。
这层就是它映射出去的基体对应的关系是什么？然后这个是两层结构没错，因为它这个是一个主要资料结构，它里面还有很多其他的，对啊，它还有很多其他要管。对啊，
什么意思？就是一个
那这个是距
离之内的各种房间，然后
对啊，没有不一样。例如，好，如果以房子为例子的话，房子里面还有分你那个灯的控制啊，有没有的？那这个单纯就只是房间的管理而已。所以这边有灯的控制、房间的控制，然后还有人没有的东西。但我这边是拿 MM 出来，就专门讲说这个房间里面的摆设应该长什么样子。对。
好，那我想问一下，就是这个如果没有这个 file 的 pointer，就是代表是 anonymous 的意思吧？
对，就是他如果没有放这个的话，
所以
就可能放 no 之类的，就是没有档案。好，
那如果是一定要增加 virtual memory address，就是一定要做这个 do and map。
对，就是如果你要扩充的话。
好，然后还有最后一个问题，是我想再请教一下这边，就是你说 thread 不会再 copy 5个，是因为它只有在 copy on write 的时候才会复制吗？
哦，不是，是因为在 Linux 里面它不支援这件事情。
在 Linux 里面不支援。
对，就是在 Linux 这个设计里面，它虽然你在做 process 复制的时候，是会把大部分都复制过来，
对，
但是就是对的资源不会直接复制5个，它只会复制1个。
就是只有 thread 不会复制全部吗？
也不能说不会复制全部。
怎么样决定我要复制哪一个业务？
就是你总会有一个队是说我要去抠，就是 fork， 就你这个 fork 指令一定是某个队去执行的。对，就看你是哪个队去执行这个。
一个 thread。
对。
好，谢谢。
打架要钱。
好啊。好，其实你可以直接寄信给我，应该比较快。可这个是可以之后再走吗？因为我看你已经有自己那个推荐信出来，还是不影响的。
他跟
哦，
放在一起。
好，没问题，谢谢。
上课说这2个是不同资料结构，但有一样的资料，那它一样资料是
一模一样的资料。
那是2份资料，然后他们不同资料结构表示，还是1份资料和不同时分区？
我想一下哦。1份资料只是它用不同的维护方式。
可是那这样我有修改的话，我不是2边同时都要修改？
哦，我懂你意思了。我想一下哦。好，我觉得我应该这样说，就是它这个的 list of memory area 就比较像是这样的形式去做，所以它基本上它的资料结构比较像是这个，然后去把它圈起来这样子，它这个连 list， 然后呢，它这个呢会把这边的形式把它改成是一个 tree 的形式，所以这边的资料是会丢不开2份出来的，那你改只会改这边而已。
没有2。
它因为这边的 VMA 变了，就是它这边对应的区域是不会动到的，对，所以它的我说的 content 一样，这指的是 VMA 这边是一样的，那资料结构是不一样的，因为资料结构是这边是因为你是用 list 去做，所以你才需要这个 next 这些东西。可是如果你今天是用 tree 的话，那你这个架构就不会有。
所以是1份资料，然后不同支撑去。
对。就是刚刚说的是，因为你 VMA 在做管理的时候，你这边好，就它这边是2种不同的资料结构去管理同样的 VMA， 因为你 VMA 有很多种存取方式吧，你可能是想要去便利所有的 VMA， 那你有可能是搜寻某个具体的 VMA， 所以如果你都用同种资料结构的话，那你就是总会有一个比较做不好的地方，所以你不如在维护的时候就维护2种资料结构，它都是对同样的一群资料在做维护，只是它是用不同的资料结构来做维护。对，所以刚刚其实我们就有讲这个啊，就是目的就是今天你如果要去那个便利所有的人的话，那你当然 list 是比较方便的，因为另 list 要找是可以这样子依序这样找。对，但是如果你今天是要搜寻某一个特定的 VMA 的话，那一定是 tree 比较快啊，因为 tree 就是漏人就可以确认可以找完。
所以算是第一个是 list， 第二个是 tree。
对。
那我又产生一个疑问，那你这个变成6，不就代表它只是复制那个 threads 吗？所以就从5变成6。 那因为你刚刚说只要是 executable instance，就是我想说就是另外一个 process，因为我以为是 process 本身要算一个，然后那个 thread 又算一个，所以现在是 process 里面的其中一个 thread， 他们是同算一个。
对啊，因为 process 等于对，因为它都是同样的执行单位，但是这个不 index 类，就是它只是不同名字而已。对，
好，
应该这样讲，就是大家的定义是 process 是资源比较独立比较多的，
对，
那对是资源比较少，所以他们都是在讲执行这件事情，执行可以被排成的单位，只是说大家对于它的那个资源共享定义不同，所以才出现这两个定义。那 Linux 在实现的时候，它是在实现层面上基本上是不会特别去区分，就是对还是这是 process 的。对，所以说我刚才讲的时候也是说，它这个其实5个里面意思是，一个你可以想想就是一个 process 加4个其他的对的，所以总共是5个。
哦，
对，
好，谢谢。
想问为什么要用这个 VM？为什么不要只是搭一个，它直接对应到 virtual memory 就好？
因为你说一个一对一嘛，因为这样找很久。就是你如果把同样的东西把它 group 在一起的话，例如你今天要在例如heap 里面找的话，可是我照你刚才讲法的话，就是我这个 cache 要找的时候，基本上我要去做维护的时候比较难维了。当然你在运行的时候是没差，因为运行的时候管那个。就这个 VMA 它是在讲的是维护的时候，我要怎么去维护出 heap 的资料可以尽可能放在一起，然后这边 BS 的资料是在一群的。对。但是你当然运行的时候，等下会讲，就在运行的时候，你就找 pay table， 那 pay table 跟这边是没有关系的。对，运行的时候它就直接看你这个 virtual address， 然后知道哪是 cache， 然后就直接会存去它。所以我在运行的时候，基本上我不会特别去区分它是 heap 还是 BS。可是我在管理的时候，因为我要知道我哪里还有基地空间可以用。我就管理，就是我今天拿到一个 allocation， 说，我 heap 要增加的时候，那我需要有一个这样的资料结构去帮助我们知道说，那到底哪里是可以再增加去。对，那这个是方便你管理的时候可以知道。这个谢谢。对。
那个也会卡比亚出来。
对，没错，对，特别也会卡比亚出来。但是那个图是上次画，就是去年画，就完全没画好。对，所以 page table 也是会 copy on right。对，基本上跟 memory 相关的大部分应该是全部资源都是同样的。hierarchy， 对，还有 copy on right。
另外一个投影片起来后看到是 red 的，自己的 address，
没有自己的 user address space。对，就是它没有下面那个3GB 那一块，它只有上面的1GB。如果以生成片来讲，
上面是共用的。
你说这些 kernel 上面是共用的？
对啊，
对，
全部都是共用的。
就是它都是指到同一块 physical， 就是这里刚好这边有，就是它都是指到同一块 physical。
不管他们是做什么工作，他们都会有样子。
可是因为kernel做的工作基本上就是管理机器，然后做一些排程什么的，所以它方选是固定在那边。
就是同样类型的工作，
因为 kernel 的行为是比较可以预测的，所以它在做就是机体维护的时候是把它放在同一块面。对。
那个要 fork
它有个叫做 k fork 嘛，就是它有个类似这种 k fork 指令，就是这里的 kernel 对其实想讲的比较像是我要去 monitor 系统资源的时候，就我可能会有一个什么那个什么 swap 低的，就是 swap 的低门在跑的时候，它去监测说我现在的什么磁碟用量如何啦，这种的。那这种它其实不是 user project， 它是系统的管理的，相对来讲它是管理的对吧？那时候它就会使用kernel对你自己去做，去出现，它就是一个独立的运行单元这样子。对。对，就是这里比较不一样。这里的 K 队，其实我觉得 kernel 队这个观点比较特别，因为它通常都是为了特殊用途而去生出来的一个队。它比较不是，就例如我举例来说好了，
那 kernel 都是用 kernel，
没有，一般 kernel 就是一般的 user process， 它执行到要 kernel 的时候，它就会进 kernel mode， 然后去执行那一块区域。所以一般的 process 在进 kernel 执行那些 schedule 的时候，不是 kernel 的人。 kernel 对指的是独立出来的某些专门拿来就是什么周期性来看一下你系统的记忆用量多少这种时候，那你会用 kernel 对，对，所以它不太一样。对，也就是说你，对，但是基本上 kernel 基本上不会有 user address space，因为就算是你刚才提到的，就是这种 scheduler 这一些，它也都是长在一般 user processor 上面那一块 HTTP 的区域而已。对，好，谢谢。All right, so let's come back. Okay, so I think let me redo this patch. So mm-users and mm-counts. Users is for number of threads and counts is for counting number of process sharing the structure. And then in an initialization phase, actually, if we have process one has 5 threads, so process one's structure will be users, like there are 5 because there are 5 threads, and count will be 1 because there's only one process sharing this structure. Okay. So then if process one forks another process called process two. So actually in Linux, when you have multi-threading, like actually you will have one thread that code the forks and to fork another process out. So this is how Linux do the thread things. So actually here I just mentioned about only the coding thread is duplicated via copy on write. So not for like all threads will be copied out. Okay. So due to this reason, process one and process two, they still share the structure because they are using copy on write. And if before any write happens, like they will still share the structure. So like users will become 6. Okay, and counts will become 2. So become 6, the reason is for process, actually in Linux, process and thread, they are very similar idea. So users, if you want to have a very kind of specific definition here, I would say like it's just like how many executable instances they are using this structure. So executable instance including like process and threads. Okay, like these kind of things. Okay, but later on, if process 2 creates 2 threads, I mean, these 2 threads usually maybe like they're using P thread, these kind of things. So the same things, process 1 and process 2, they still share the same structure because there is no update on the VMA part. So users now becomes add because you have 2 more threads, and you can see the breakdown will be 5 from P1 and 3 from P2. Okay. And then counts still remains 2 because there's no process created. Okay. Okay. So thread share structure with its parent process. So this is just let you know, like actually threads, they will share the structure with their own process. So now if process 1 adds a VMA, so maybe process 1 calls the do-mm, and then the structure should change, right? Because if we call do-vma, then one moment. Then if we call do-mm, then this star mm probably will get another VMA, and then the VMA structure would have insert one more VMA here with its new VMA start and VMA end. Okay, so this structure will be updated. And because this structure is updated, so the whole structure will be copied out for process 1. Okay, so in this step, because there is a write, so we do the copy. Okay, so after doing the copy, actually process 1's the users becomes 5 because in the prior stage, like if we do the breakdown, process 1, you have 5 users here, right? Because at the very beginning, we say process 1 has 5 threads, and then counts becomes 1. and because like process 1 is one process, okay? And process 2, MN counts also has 1 because this MN dash structure is belonging to this process. And then there are 3 threads. So MN dash users will become 3. So 3 threads this is the same reason for this one, because like process is also a user, okay, like this. Okay, so updated VMA field triggers MN dash structure copy, then we will do the copy on write. Okay, then the MN dash structure will become 2 structures here. Okay. So one moment. Okay, I think there is some misleading here. So actually, there is someone asking about like in this example, like here is, oh, maybe this is better. So here are several fields here, right? And this is the VM area structure, right? So inside this structure, there are some VM start, VM dash, VM next. Okay, so actually, there are more fields here. So I think this figure is a little bit misleading, but I just want to let you know, like this probably will be one field. So I think this will be more than 4 fields. This depends on how many fields they are. Okay, so this is just for the indication part. Okay. Okay, so this is for the VMA management part. And like, okay. So next on, let's talk about some basic concept of memory management. Let's come back to talk about what is patch table. Let me give you a very brief introduction on patch table before going to the details. Okay. So here, so when the CPU is going to access the data on the memory, usually, or like in our modern systems, CPU will first get a virtual memory, the virtual address first. Okay, so each virtual address should first go through the TOB to find if there is a hit inside TOB. So if there is a hit, means there is already a translation result between this virtual address and the physical address. So if there is, then CPU can directly access the memory. But if it is not in the TOB, then CPU should walk through the patch table before accessing the DRAM. So you can think about if there is not in the TOB, then MMU will come to walk the patch table and then do the translation here. After doing the translation, CPU can access the patch data according to the physical address. So this is the brief concept about the patch table things. So you can think about patch table just like a translation things between the virtual address and physical address here. So for systems with virtual memory management, or like for system having MMU, all virtual address should be converted to physical address before being accessed. So for each instruction that CPU get, it is virtual address. Okay. So patch tables take the responsibility for address translations. Okay. So each patch table comprises a bunch of add byte patch table entries. So for sure, patch table entries is PTE. So add byte is because currently I assume we are using the 60-bit systems. So 60 bits equals to add byte. Okay, so one PTE entry means 64 bits. So it means add byte. Okay. So the size of patch table is proportional to the memory size. So if you have larger memory, like if the process used larger memory, more memory, then there will be more PTEs. So one PTE means there is a translation between the virtual and physical. Okay. So Linux used the multi-level patch table here. And there is 4 level for the 64-bit systems. And I'll let you know why this is 4 levels, not other kind of labels here later. So I think one tricky thing is actually each patch table entries, they are also stored on the DRAM. So you can think about this is our DRAM, right? And here, each one is a patch frame, 4 kilobyte patch frame. So patch table is also stored in a patch frame. So inside this patch frame, there are 4 kilobyte, and you can 4 kilobyte divided by add. So maybe they are 512. There are 512 patch table entries here.
Okay, so you can think about here's the first entry, second entry, third entry, and there are 5 tail entries in this patch frame. Okay, so this is about the patch tables things. So without optimization, CPU should access memory for looking up a patch table each time. Okay, but it is time consuming. The reason is if each time we need to do the translation, it means CPU each time should access the memory. Okay, but each memory access is usually 15 nanoseconds, or like it is around like 10 to 15 nanoseconds. But for CPU itself, it only needs 0.3 or even lower nanoseconds to finish one instruction. So if CPU frequently do the address translation, and then if each instruction it needs to first do the address translation, then you will take a super large overhead to do this kind of stuff. So this is why in this TOB. And TOB is a hardware cache to keep the mapping between the VA to PA in the CPU. And TOB usually is not DRAM. TOB usually is a faster SRAM. So TOB usually only needs kind of 1 to 10 nanoseconds. Usually it's 1 nanosecond. So it is kind of like 50 times faster than DRAM. Okay. So this is how TOB is so important in the CPU design. Okay, so CPU raise a patch. Oh, I think you will be a little bit curious about why we talk a lot about CPU now. Because when you are going to do the patch table walking, actually in most cases, operating system will not help on the patch table walking part, because CPU will directly walk the patch table. So this is the reason why in this stage, I'm going to let you know a little bit more about how CPU works. Okay, so CPU raise a patch fault when a process accesses a memory patch without proper preparation. So like this, there are two kind of patch faults. The one is minor patch fault. Minor patch fault means patch is already in the memory, but it's not marked in the CPU. So it just means like the virtual and physical address doesn't really link together. Okay, so this is the minor patch fault part. So for example, when you use a memory allocation to allocate a super large area, so depends, maybe you can say, hey, I want a 1 gigabyte area. But actually, Linux will not directly, oh, sorry, it's not Linux. The C library will not directly give you 1 gigabyte. Because if everyone say it needs 1 gigabyte, then the memory will be very limited for all the users. So only when you really touch the memory will be allocated. So current system use the on-demand patching. On-demand means you really access the address, then operating system will allocate the patch to you. Okay, but I think this is not that accurate because not really the patch is not really allocated from the operating system. Because if you guys, let me do a little bit deeper dive into this part. Because when you are going to run your C program, actually there is a library, right? So your memory allocation, usually it interacts with the library, not the OS kernel. So you can think about is the library will first allocate a super large memory from the kernel. For example, maybe the library will first get 1 gigabyte from the kernel. But because this is a shared library, so maybe there are 10 processes that are using the same shared library. So when one process say, hey, I want kind of 10 megabyte, and it really uses 10 megabyte, then the library will allocate 10 megabyte to that process. Okay, so you can think about actually current programming library takes a lot of efforts on those kind of stuff. Because if each time each process is going to access the operating system, then the system performance will be so low. Because each time you are going to access a kernel, you need to switch into kernel mode and you need to do a lot of kernel management things. But if library can help you to cover most of the things, then library and user process, actually they are all in the user space. You don't really need to do the CPU mode switching. Okay, so actually this is a little bit more details about the user process and kernel. Okay, so how about measure patch fault? So measure patch fault is usually is what you learn in the undergraduate. Is the patch is not in the memory, so probably it is in the storage device. Okay, so in this case, there will be extra expensive I/O movement codes for the measure patch fault. So because measure patch fault usually takes longer time than minor patch fault, so it is called measure. Okay. Okay, so I think this is the most important part for the virtual memory, just like how the CPU works patch table. So let me directly give you one example, and maybe you will be more kind of have more knowledge about how does it work. So let's take 64-bit system as an example. And actually, even we have 64-bit systems, that means we can address in 2 to the 64 byte. But if you do some calculation, 2 to the 64 is super huge, right? Because 2 to the 64, usually people will not use that much of memory. So in current system now, usually you only use 48 bits. But 48-bit is still super large because 2 to the 48 means there are 256 terabyte of memory. So 256 terabyte of memory, usually, no matter you are using PC or servers, you're not really use that much of memory. So it is enough for current systems for using only 48 bits. Okay, so the reason why we don't use 64-bit, later you will know, because the more bits you are using, it means you need to access DRAM for more time. So fewer bits will be better, will give you better performance. Okay, I think I will explain this later. So in this example, here is 64-bit, and from 48, upper than 48, there are all unused bits. So from 48 bits to 39 bits, there are 9 bits for like PGD offset. Okay, and then 39 bit to 30 bit, they're called PUD offset. So actually PGD and PUD, they are all patch table, but there are different class of patch tables. So PGD is one class of patch table. Okay, it is called like, I think it's kind of patch global directly, something like that. And this is upper directly, middle directory, and this is patch table. And then there is patch table, there are patch offset here. So this is one level. The first level of patch table is PGD. And the second level of patch table is called PUD. And the third one is called PMD patch table. And the fourth one is patch table. Okay. So you can see like patch offset is because here are 12 bits of patch offset. So 12 bits means there are 4 kilobyte, right? 2 to the 12 is 4 kilobyte. Okay. So this patch offset is going to address like inside the patch. Just like if this is a 4 kilobyte patch, then we are going to get the first like 1 gigabyte. Then this offset is going to use to get that part. Okay. Okay, let's start from. Okay, so how CPU can work the patch table without the help from operating system? So actually, CPU doesn't need the help from operating system. CPU can do the patch table translation. Okay, so here, the key thing is there is a register in CPU called CR3 register. So CR3 register will store the base address of PGD. So what I say there is a base address is like here, PGD here is a patch table. So if we are going to get the patch table, we need to know where is the beginning, where is the start of the patch, right? As we mentioned before, each patch table is also stored on the DRAM. So we need to know the location here. So CPU can work automatically, and kernel code can also work it. So there are 2 ways to work the patch table. So in this example, I only explained how CPU can work automatically, because I think in the kernel code, it'd be easier, because kernel, you can use a lot of software things to do this kind of patch table working. But CPU, there are only hardware things that they can use for working. So it is, I think CPU is a little bit harder to work the patch table. So first of all, PGD base address, it will be stored in the CPU's CR3 register. Okay, so with this register, actually you will point to the bottom of the patch global directory table. So this is the first level patch table, right? So with this PGD offset, actually we can locate which PGD entry it is. So if you still remember, each entry is only 8 byte. Okay, so this 8 byte. Okay, so this 8 byte actually you can use to get the next level patch table where it is. It is possible to locate where is the next level. So the next level will be on the bottom of the patch upper directory. So this PGD will store, hey, where is the address of the PUD? Okay.
So after getting the PUD, actually there is a PUD offset here. So the offset is going to locate, okay, so where is the next label is. So PUD offset plus this best address here. Like you can get the PUD entry. So after reading the PUD entry, you will get another 64 bits. Okay, so for this 64 bit, you can get the bottom of the patch middle directly again. Okay, so with this PMD table, you are going to know where is the next label is. So you're going to use a PMD offset again. So with this PMD offset plus this PMD entry, then you can get a PMD entry here. Okay. Oh, I think here is one thing to let you know is how to do the location inside this and why there are all 9 bits. So 9 bits is because, as we say, PMD entry, PUD entry, PGD entry, they're all patch table entry. So they're all 8 byte, right? So there are 512 patch table entries in each patch table. So if this patch table is 4 kilobyte, then for each 4 kilobyte, you can have 512 8 bytes here. So if you are going to know where is the location or position for each entry, you need at least 9 bits, right? Because using 9 bits, you can do the 2 to the 9 location, right? 2 to the 9 is 512, right? So using these 9 bits, you can know where is location for this 512 page table entry. Okay. Okay. So you just look through the 4 layers because this is the last level here. This is also 9 bits here. So with the PMD entries and then offset using the patch table offset here, you can get to the last level called the patch table. So inside the patch table, inside the patch table, you can find the last patch table entry here. Okay, but this entry will only point to a patch, right? Because each entry will only point to a patch frame. So this entry is pointing to the patch frame owned by this patch upper directory table. And this entry will point to the patch frame related to this patch middle directly. So actually, each of the patch global directory table, this table and this table, they are super huge. They are several hundred or thousand of patch frames there. Okay, so each entry will point to a different patch. Okay, so when you come to the last level here, and you get the patch address, you will directly point to a patch, right? But if we are going to know where is the data that we store in the patch, we need the last level, the patch offset here, right? So this patch offset will be 12 bits. The 12 bits, the reason for 12 bits is we are going to address in the 4 kilobyte. So 4 kilobyte, we need 12 bits, 2 to the 12 to do the addressing. So like this. After opening the patch table entries, you will see this is a 64 bits, right? Because this is 8 bytes and here is 64 bits. And then the same things, this 64 bits, actually, there are the lower 12 bits with the control bits. And then the 12 bits to the 48 bits is the physical address. And then this is reserve. So this reserve is just like this because this is unused. Okay. So physical address here is about the 48 bit to this 12 bits. Just like we are going to do the virtual to physical translation. So here is the physical address here. And then the very beginning of the 0 to 12 bits here, it will be concat together with this patch offset. So you can think about this patch offset will be placed here, replace these control bits. Then from this 0 bit to this 48 bits, it can become a new physical address. Okay, this physical address will directly point to the DRAM. Okay, so this is from given a virtual address. This one is virtual address, and then this is physical address. Okay, so we're done. We're done doing the translation. So there are 4 label translation. The first is this label, second is PUD, the third is PMD, and the fourth is patch table offset. So in this procedure, in the whole procedures, we don't really need solver, right? So all the things can be finished only using the hardware part, right? Because each part, like you get a PGD bus address, is because inside the CPU there is a register here. So this plus here, the PGD-offset, this function, actually this is not a solver function. This one is only, you are going to replace this 64 bits. You are going to replace the very beginning 9 bits by this 9 bits. Okay, so you just like do some dropping, and then you can just replace this 9 bits to the tail of this, like this bus address. Then you can get the address here. So actually, this is what MMU really does. MMU is not really a very complex. It's not a really complex kind of hardware structure. Actually, it's just a very simple circuit to concatenate the address together. It concatenates this 64 bits with the 9 bits. So the very beginning of the 9 bits will be replaced by this PGD offset. Okay, this is what MMU does. Okay, so another thing to let you know is, so why I emphasize a lot about this CPU CR3 register is so important, because if you still remember, for patch table is each process has their own patch table, right? So if you are going to context switch to other process, you need to switch the bus address. So during the context switch, there is one step is to replace the bus address by maybe the other process bus address. Okay, so for each patch table, for each process, they have their own patch table. And this patch table, there is a bus address to be the very beginning to start the traversal. And the beginning will be put into the CPU CR3 register. Okay, so this is how it works. Okay. So there is another thing is about, how about the control bits here? So actually control bits, there are several control bits here. Actually, one of the control bit is called the present bit. This is important because this is how CPU triggers patch flow. Okay, so after doing this translation from virtual memory to physical, from virtual address to physical address, actually the data is still there. CPU still doesn't really access the data. CPU only get the physical address, right? Because this is just a physical address. So CPU doesn't really access the DRAM. And before accessing DRAM, CPU will first check the control bits. Inside the control bits, if the present bit is not set, because present bit means if the data is presented inside the DRAM. So if the present bit is not set, it means the data is not in the DRAM. Okay, so if the data is not in the DRAM, probably it is in the storage device. So there is a major patch fault here. Okay, so this is how CPU triggers patch fault. CPU will check the control bits and to check about if the data is in the memory or not. If it is not, then there is a patch fault. Okay, so this is how the patch table working looks like. So I think it's a little bit quick. So do you need to do it again, like to run through the whole process again, or maybe you guys already understand about it? Okay, so maybe I'll quickly go through it again and then to make it a little bit clear for this part. Okay, so again, so if this is a 64-bit systems, then you have, for each address, it will be 64 bits. So for each time CPU going to run an instruction, probably the instruction would need to access some data or something else. Then the data is in a virtual address. So CPU every time will get a virtual address. And CPU needs to know where is the physical address. It means CPU needs to know where the data stored on the DRAM. So CPU needs to do this virtual to physical translation. Okay, so at the very beginning, CPU will read out the bus address from its CR3 register. So this bus address is also a 64-bit string. Then these bit strings will point to the button for the first level. I mean, the first level of the patch table. So PGD bus address will point to the bottom of this patch table. Okay, but inside this patch table, actually, this patch table is stored on a 4 kilobyte patch frame, right? Inside this 4 kilobyte patch frames, there are a lot of patch table entries. There are a lot of PGD entries. So one of the entry will be add byte. So there will be 512 PGD entries here. So if we are going to know where is the entry that we really need, then we need to read this PGD offset out and then do the concatenation. So concatenation is look like this. Like this is the 64 bits. So the last 9 bits will be directly replaced by this PGD offset. Okay, the reason is from 64-bit to the 9 bits is used for locating where is the patch frame is. But inside the patch frame, we still need to know where the patch table entry that we are needing now. So this 9 bits is going to navigate where is the correct patch table entry that we need. So in this example, with the help of the PGD offset, we can know, oh, this is on the second PGD entry that we are now needed. So CPU will then read out the patch frame from the DRAM and then read out this PGD entry and then do some decoding things. And then CPU will know, hey, actually, inside this PGD entry, there are another 64 bits. Okay, so for this 64 bits, actually, again, the same things. The prior 48 to 9 bits will be point to a patch frame. So this patch frame stores the second label of the patch table. The second label calls the patch upper directory. So inside this patch upper directory, actually, there should be a lot of patch frames because this table will be super huge. And in the next slides, I'll show you how large it is. And then with this PGD entry, we can know where is the patch frame it is. So we find the corresponding patch frame, and then the next question is, actually inside these patch frames, there are a lot of entry, right? So we need an offset. We need an offset to navigate where is the correct entry that we need. So with this PUD offset, we can concatenate with this PGD entry again. So with this PUD offset, we can know, hey, actually the PUD entry is this one that you need. So the same thing, the PUD entry is a 64-bit bit streams. It's a 64-bit address. So this address is pointing to the third label of the patch table. And the same things, actually there are so many patch frames related to this patch table. So we need this entry to point to where is the correct patch frame that we need now. So for this patch frame is another 4 kilobyte, and inside there is 512 patch table entry. And this time we need to navigate again. So we use this PMD offset to navigate where is the next label is. Okay, so with this navigation, we can know, hey, actually this is a PMD entry that we need now. So we do the same thing, we decode it, and then we get to the last label, the patch table. So inside this patch table, actually, we still need to know where is the correct entry it is. So we use this offset to get the correct entry. Okay, so after you open this entry, I mean, they are the same. I mean, the format there will be the same. This entry, actually, they look like these things. There are 64 bits. Because I say this patch table entry, they are all 8 bytes. So for this 64 bit, for each bit, they will have different meanings here. And from 12 bit to 48 bits, it stores the physical address. Okay, so maybe if you are very confused about the prior one, actually the PGD entry, if you open up from the 9 bit to 48 bits, it is the physical address. This physical address will be pointing to the base address of the PUD table. Okay, so the thing is, because there are 0 to 12 bits, and this 0 to 12 bit actually is used to navigate where is the data inside this 4 kilobyte patch, right? So this 48 bits we're going to use as a physical address. So using this 48 bits, we can directly point to the byte in this patch. Okay, but this information can be get from this patch offset. So actually inside the patch table, we don't really need to store this part, right? We just need to know which patch it is. So this one, physical address from 12-bit to 48-bit, can only point to the patch. Okay, but inside the patch, we need the first 12 bits, and this is the virtual address can provide to us. So using this patch offset, we replace the first 12 bits, then we can get the byte inside of on the DRAM like this. So we can get the data out. Okay. So the thing is, actually, because the first 12 bits that is not really required for in a patch table. So Linux developers thinks like maybe we can play some tricks on these first 12 bits. So for each bit here, actually there are some meanings here. For example, there is a present bit. Usually just only one bit here, just like 0 or 1. If it is 0, it means the data is not in the memory. If it is 1, it means the data is in the memory, like this. So not only present bit, there are also like 30 bits. So 30 bits just like if this patch is 30 or not, if this patch is updated or not. So if the patch is updated, then it needs to somehow need to be right back to the store device. So there is also 30 bits. And there are also a lot of other control bits, but I think it's not important for this class. So I just put the present bit here to let you know each bit there is a meaning for the patch table entry. So that is for the like how to work the patch table. Okay. Let me check how much time we have now. Okay, 10 minutes. I think it's enough. So any question for this one? I mean, for the online part, I think there are a little bit too many questions, so I will arrange it and then answer it next time. Yep. So for guys here, any question for the patch table working? Okay, so if it is clear, then let's go to the next slide. So why it is 4 label? I mean, why not 3 or like why not 5? Oh, actually it can be 5, but the reason is for each time we say we have this concatenated address will point to the DRAM. Actually, each time the CPU needs to access DRAM. So you can image if we are going to do this virtual to physical address translation, we need at most 4 DRAM access, right? So each DRAM access will take 50 nanoseconds. If you are going to do 4, it means you need 200 nanoseconds. And this 200 nanoseconds cannot be due in a parallel way, because without getting the prior stage, without getting the prior label, you cannot get the later one. So you need to do it one by one. Okay, so it will be super expensive if you are going to do the patch table translation every time. Okay, so the reason I say at most 4 is because actually in the MMU there are several caching design. So probably it is possible like you only need to do the first 3, and the last part it is stored in a cache of the MMU. But I think this is quite too more details. So you just need to know each time when you are going to get a patch table, it is 1 memory access here. So if this is not 4 label, it is 5 label or like 6 labels, then you need to do 5 times or even 6 times of the memory access. And you probably need to do the virtual to physical address translation every time when you are going to run, when you're going to execute an instruction. Okay, so you will take super long time. Okay, and the question next is why not just not use like 3 label or 2 labels, or like why not just use 1 label? Okay, so the reason is here. So let's assume the page size is 4 kilobyte and there's 212 byte here, and the virtual address space size is 2 to the 48. So this is the virtual address size, 48 bits. So we have 2 to the 48 bytes that we can use for addressing the virtual address. And the patch table entry size is 8 byte, right? Okay, and there are how many labels? So the key idea for this to decide how many label is here. Actually, we need to know where is the first label, right? Without knowing the first label, we cannot know the later label. Okay, but how to know the first label? I just say like we store the base address inside the CPU, right? But if the first label is stored in several patch frames, then we will need a lot of register here, right? Because each register can only store 1 address. So 1 address can only point to 1 patch frame. So the key idea is the first label should be possible to fit inside 1 patch frame. It cannot be more than 1 patch frame. It can only be less than 1 patch frame. So the first label, the size of the first label can only be not more than 4 kilobyte. Okay, so this is the things that we are going to do the calculation. So like this,
let's first calculate the last level. So how to calculate the last level? Like given this virtual address space is 2 to the 48, then for this 2 to the 48 virtual address space, if we divide by 2 to the 12, it means we can have that much of patches here. Okay, so 2 to the 48 divided by 2 to the 12 is 2 to the 36. So we have 2 to the 36 patch frames for the last level, right? If we are going to address in 2 to the 36 of the patch frame, then we need this large of the patch table entry size, because each patch table entry can only address one patch frame. So if you have 2 to the 36 patch frames, you need 2 to the 33 times 8 byte of the size of the patch table entry. So this is 2 to the 39 byte. So with this huge size, actually it's more than 4 kilobyte, right? 4 kilobyte, there's only 2 to the 12 byte. Okay, so this will not be this cannot be the one label patch table translation. Okay, so let's see like this. Here is 4 kilobyte patches. Then we have 2 to the 36 patches, because 2 to the 48 divided by 2 to the 12. So you have this much of the 4 kilobyte patches. But as I say, if you are going to use the CR3 to point to the base address, it should only be one patch table. Sorry, the patch table should only be stored in one patch frame. It cannot be that much. Okay, so this is the PTE used to address this patch table frame. So there are that much of PTE. Okay, so because this kind of PTE cannot fit in one patch table, so we need the next label. So the next label, like you divide by 2 to the 12 again, and then you time add, like you have this much of the patch table, right? So there are 2 to the 27 patch table. So each patch table needs a patch table entry. Okay, so actually the patch table entry overall for the second label will be 2 to the 27 times add. That means 2 to the 30 byte. So 2 to the 30 byte is still way larger than 2 to the 12. So we need the next label, because this cannot still be fit in one patch. So the next label, we do the same thing. We divide by 2 to the 12 and then time the patch table size, sorry, the patch table entry size. So we can get the third label. So the third label is 2 to the 12, sorry, 2 to the 18 patch table here. And the PTE size is 2 to the 21 byte. So 2 to the 21 byte is still a little bit larger than 2 to the 12, but it is close. So we do another label again. So another label is like this. So the last 4 label, if you do the, sorry. So if you do the calculation, you will get, hey, actually, there's only like 2 to the 9 patch tables here. So 2 to the 9 patch table, you only need 2 to the 9 patch table entry. Then each entry is 8 byte, right? So 8 byte times 2 to the 9 is 2 to the 12. So 2 to the 12 can fit in one patch table, right? So we're finished. We're done here. So this is the reason why we need 4 labels. And because the last label, or like the first label, can be fit inside one patch, so we can use the CR3 to point to this label. Okay, so this is how the overall translation works like. No, not translation. Why we need 4 label? Okay, is it clear? So let me do it again, because this is a little bit complex. So once again, if we are going to decide why this is 4 label, then we need to know, because the full translation, it starts from the base address, because CPU only use one register to store the base address. And this base address can only point to one patch table. So the first letter, I mean, all the PT related to the first label patch table should be fit in one patch frame. Okay, so this is what we are going to calculate. So let's start the calculation. So if our virtual address space is 2 to the 48, then we are going to know how many patch table we are needed to address this virtual address space. So 2 to the 48 divided by 2 to the 12 is here, is 2 to the 36 patches. Okay, with this 2 to the 36 patches, actually for each patch, we need this amount of PTE, because each PTE can only address one 4 kilobyte patch. Okay, so 2 to the 36 patches, sorry, 2 to the 36 PTE. So each PTE is 8 byte. So the overall size is 2 to the 39 byte. Okay, but 2 to the 39 byte is way larger than 2 to the 12 byte because our goal is to fit all the PTE in one patch frame. Okay, so one patch frame is 4 kilobytes, 2 to the 12. So 2 to the 39 is larger than 2 to the 12. So it is not possible to be the last level. Okay, so let's move on to the last two level. So last two level, we do the same calculation. If we divide by 2 to the 12, we can now get, we need 2 to the 27 patch table, right? Okay, so for this 2 to the 27 patch table, for each PTE, actually is 8 byte. So we need 2 to the 30 byte of the PTE. Okay, but 2 to the 30 byte of the PTE still cannot fit inside one patch frame. So this cannot be the top level. So once again, we we divide by 2 to the 12 bytes, and then we times by 8, we're going to get the third level. So the third level of the PTE overall needs 2 to the 21 byte. Okay, but 2 to the 21 byte, those amount of PTE size cannot be fit into one patch frame. So once again, we do the partition. So we are going to store them inside the patch table. So actually, we need this much of patch table. Okay. Okay. Oh, sorry. I think this is not clear. I think I need to modify this patch table to patch frames. I think patch frames is a better fit here. Sorry, I think I will do some modification for this terminology. I think patch frames are easier to understand in this case. Okay. Okay. So for this amount of the 2 to the 9 patch frames, each patch frame we need 1 PTE. Okay. So overall, we can get 2 to the 12 byte. So 2 to the 12 byte is equal to the patch size. So this table, the whole amount of PTE can be fit in one patch frame. So we can use one CR3 register to point to the best address or like the first address of this patch frame. So in this case, we can know there are 4 labels here. Okay, at least we need 4 labels. I mean, it is possible to use more. You can use 5 labels or 6 labels. Okay, but at least you need 4. Okay, so this is the calculation here. Okay, I think there's only 1 minute left. It is not possible to do this advanced topic. So let's stop here and then, yeah, see you guys next week.
今天有人帮忙那个吗？记那个档次。
登记是那个地方。
哦，好，应该有人帮忙，还是你先问好了。
我想问一下，所以这里是只会有一个 patch table，然后这边会有多个 patch table。
对，
哦，
对。
所以好。
我觉得应该，我刚才讲不太好，应该说这个 patch table 只需要一个 patch frame。
哦，对。
对，那这边它是也是一个很大的 patch table，只是它会存在好几个 patch frame 里面。
哦，对。
这样讲可能比较好一点。对，我刚才再讲八仙应该这样讲比较好。
那我可以再问一下，为什么这是12 bits 吧？我知道9 bits 是因为每个 patch table 只能有512个这个 entry 嘛，那为什么这个是12？
因为它要定位这个4K byte 这个配置里面的每一个 byte 是在什么位置，然后4K byte 就除以 byte，所以你需要4096。4096的话，你需要12 bits。哦，就定了。对，
好，谢谢。
我想问前面这个 memory descriptor 的东西，所以这东西是放在那个 process descriptor 里面，
是从 process descriptor 可以连到的，
可以连到的地方。
那往下连到。
那假设我好奇的是，就是这些资讯它是存在哪？因为
存在哪里？存在 kernel data structure 里面。
所以它是 kernel， 这些全部都是 kernel mode 里面的东西。
都是 kernel address space 上面的东西，就是这里。就是所有 data structure 基本上都存在这个地方。你看那 kernel stack， 然后 MN structure， 然后那些 hex structure， 对，
都是存在这个地方。所以当我今天假设我要 context switch 的时候，它就会先去 access 这个 kernel mode 的，然后去 figure out 每个这个
VMA，然后让它去组成新的一个 virtual address。
应该不用，
不用，
因为它这个地方其实是我觉得应该这样说，就是这个东西只是用来管理而已。就这个 process 它需要的 virtual address space 还有剩下多少？对，所以如果你换个 process 的话，它这个 data 会整个换掉，就你的 text structure 就不一样。所以 text structure 会直接拿到另外一个 process 的 virtual memory area， 那你就可以知道说它现在有哪些地方上还没被分配的。
那
其实
说，如果我换了一个 process 之后，我怎么知道我的现在的 virtual address 是长怎么样子？
就是你会需要透过这个它存在这个里面，因为这个里面的要装选基本上是不太换的。就是所有的 process 的资讯都会存在这里面。对不对？对，所以你就算换了一个 process 资讯，那你还是可以从这里面拿到。顶多就是你要换 process 资讯的时候，你就把那个 process 相关的再从就是其他地方把它拉进来。因为这个地方是大家共用的。这一区是所有 process 对，所以基本上所有 process 相关的都会放在这一区。
然后把它拉进来到这。
对，等我一下哦。好，那个线上同学，因为下个课程老师来了，所以我先结束一下。问题我就下周一开始我再回答各位。等一下哦。我们去外面好。谢。